A warm welcome to all of you in this last lecture of the course Processing of Non-Metals. As we have been discussing module number 7 for the last 1 week, we have now come to the lecture number 5 of module number 7. On your screen you can see the title of today's lecture, that is Research Tools for Secondary Processing. If we focus on what we have discussed in this course on processing of non-metals, we have seen so many different techniques of processing a wide variety of materials ranging from the ceramics to the polymers, to the polymer matrix composites, to the ceramic matrix composites. So, we have seen a large number of techniques which are used for processing of these materials or these specific materials. But towards the end we have discussed module number 7, in which we have already discussed 4 lectures where we have seen what are the problems, what are the issues and challenges associated with the secondary processing of specifically composites. We have seen what are the problems that arise when we try to make a hole inside a composite laminates. If you remember, we have seen there are so many tools and techniques which have been proposed to avoid this damage. We have also seen that what are the problems associated with the joining of the composite members and how these problems can be avoided, or the efforts that have gone into research for avoiding the issues associated with the joining of polymer composites. So, we have seen the how microwave joining is done and how it overcomes some of the limitations of the adhesive joining and the mechanical fastening. So, all these techniques have been discussed, but still a wide gap exists in specifically in the field of secondary processing of polymer composites, because if you see the overall structure of the course also, we have seen 35 lectures broadly dedicated towards the engineering materials, their manufacturability, as well as towards the manufacturing techniques or processing techniques for a wide variety of materials that fall under the broad umbrella of non-metals or those materials which have properties similar to the non-metals. So, we have seen that a large number of techniques exist to produce or to process these materials in a most cost effective and qualitative manner, and we can ascertain good quality products also. But a lot remains to be done towards the secondary processing, because most of the products made by these materials are put to direct use without any secondary processing. But in our last 4 lectures, in every lecture I have given an introduction that why secondary processing is required. So, just to brief you once again, and for those people who are only listening to this particular lecture, secondary processing in advanced materials or composite materials is required because the parts that we make by the primary processing or the conventional methods have to be assembled together to get the complete structure. So, to facilitate the assembly operations, many a times secondary processing in terms of drilling or joining is required so that we get the complete product. So, secondary operations sometimes are completely unavoidable and they are necessary to ascertain the structural integrity of a complex composite part. So, basically today our focus would be to see on the research tools, that what are the various tools that can be used to solve certain problems associated with the secondary processing of the polymer composites or the total composites family in general. So, as the time permit, we would see 3 important different areas in today's lecture, that is we will see the simulation of or the finite element modeling of the drilling process specifically in case of polymer composites. Then we will see the microwave joining, how the process can be investigated using the finite element method, and towards the end of today's lecture I will just give a brief overview of the various methods which can be used to predict the forces and the drilling induced damage in case of drilling of polymer composites. So, basically our focus would be on the tools and the application would be the secondary processing of polymer composites. So, we would be just highlighting the tools, that which tools can be used and what type of results can be got, without going into the much detail of one particular area. So, it would be an overview where we will see that what type of analysis can be done in case of secondary processing of polymer composites. So first of all, we need to understand that why we need to go for secondary processing and what are the problem areas associated with it. So I have already highlighted the need of secondary processing. Again, I want to emphasize the need of secondary processing is because we want to get a complete structure made up of different parts, and the parts needs to be assembled together, and to facilitate the assembly operations, secondary operations are required or secondary processing is required. And in secondary processing, one of the important processes is drilling. So we will see that in case of drilling, why it is important to investigate drilling in much more detail. So we will see that what are the input parameters in drilling, what are the output parameters in drilling, and how complex is the whole process, and why do we need to use these research tools to investigate the drilling behavior of polymer matrix composites. So with this introduction, now let us start our lecture today. On your screen you have a simple diagram in which there are two broad categories. We have an input and we have an output. Now what is the input? The input, and this particular diagram gives us the inputs and the output relationship in case of the drilling of polymer matrix composites. So drilling of polymer matrix composites means the process is drilling and the material is polymer matrix composite. So we can see there are broadly three inputs going into the process. This is the drilling process. In the process there are broadly three inputs: input number 1, input number 2 and input number 3. Now what are these three inputs? Input number 1 is the operating variables. Now in drilling process, what are the operating variables? The operating variables are the cutting speed and the feed rate. There are two operating variables primarily that are going into the drilling process. So operating variables, cutting speed and feed rate. Drill parameters. Now what are the drill parameters? Drill parameters are the drill point geometry, the drill diameter and the drill materials. So there are three important parameters those govern the drilling parameters or related to the cutting tool, or the twist drill is one type of a drill point geometry. You can have different types of drill point geometry. So basically the second input that is going into the process is related to the cutting tool. First input that is going into the process is related to the machine tool. Machine tool, basically we have a drilling machine, and in drilling machine we can control two parameters, that is cutting speed and feed rate. So first input is related to the machine tool, the operating variables of the machine tool. The second input is related to the tool or the cutting tool, that is the drill. So we can have drill parameters like what is the geometry of the drill, as I have already highlighted. Twist drill is one important type of drill which is used for making holes in materials. Then we can have the diameter of the drill and the material of the drill, the tool material. So our focus is on tool geometry, tool material and tool diameter, which will be acting as the drill parameters which go into the process. And finally we have the material parameters, that is the material parameters that go into the process. So the material parameters is specifically in case of fiber reinforced plastics are fiber types, fiber volume fraction, stacking sequence and matrix types. So we have four important material parameters which go into the process. Once again we will revise. Fiber types. We have seen in our lecture on polymer matrix composite that different types of fibers can be used, which can be natural fibers also, synthetic fibers also. Within synthetic fibers we have seen there is a category of fibers which can be used. To name a few of the fibers, in both the categories we can have glass fibers, carbon fiber, aramid fibers, we can have hemp fiber, sisal fiber, nettle fiber, grevia optiva. Within these categories, natural and synthetic, we can have a large variety of fibers. So one important point is the fiber type. Another is the fiber volume fraction, how much fibers are there in the composite. Stacking sequence, what are the different layers in the laminate or the composite laminate, how the various layers have been stacked together to make the composite laminate. And finally the matrix type. Broadly the matrix types can be classified into thermosets and thermoplastics, and within thermosets and thermoplastic we have a huge variety of other types of polymers which can be used as the matrix material in order to make the composite material, which we have already seen in module number 5. We have seen large number of processes which are used to combine the matrix and the reinforced reinforcement to get the final product. So input side we have, you can see, so many things that we need to control in order to fully characterize the drilling process, or to simplify, to fully understand the drilling behavior. So if we have one type of a fiber, one type of a matrix, and at single speed and single feed, using our simple tool point geometry made up of a simplest of tool material, we make a hole. A slight change in the input parameters would certainly change the drilling behavior of the second hole that we will make by changing the parameters. So there are so many input parameters which go into the process, and then the process gives us output in terms of, we can see what are the various outputs from the process. Outputs are thrust force, torque, and drilling induced damage. So basically, when we have a large number of inputs that go into the process, we get an output. The output can be recorded in the form of thrust force and torque. So we need to understand that these input parameters, when they go into the process gives us an output, and the output has to be correlated to the input parameters. We should know that if this is the setting, these are the operating variables, these are the tool variables or tool geometry or tool material or tool diameter, and this is the material of the workpiece, that is, suppose it is glass fiber and epoxy matrix, we should be able to understand and very easily tell that this much thrust force would be generated or this much torque would be generated, and the damage would be less or more. So basically we have a set of input parameters, we have a process, and finally we get a output. So these input and output have to be somehow matched, and an expert should be there who should be able to correlate these inputs with the outputs. Now what are the decisions that need to be taken? Now we know that we have a set of input parameters which will go into the process, and the process will give us some output. Now in order to get a good output, what should we do? Always we want that the forces should be less, the damage should be less. Now for minimum forces and minimum damage, what are the decisions that we need to take? On your screen you can see these are the decisions that we need to take. These are the decisions. We should optimize the cutting speed, we should select the optimal cutting speed, optimum feed rate, optimal drill geometry. Suppose we have 10 different geometries which can be used to make a hole, we should select the most optimal one which will give us the best quality hole. And we should select the drill material also, because we have seen in the previous lectures different types of tool materials can be used to make holes in composite laminate. So we should select the optimal tool material, optimal tool geometry, optimal feed rate, and optimal cutting speed, so that we get a good quality hole. So these are the decisions that we need to take. Then there are some variations in the process that we have seen in lecture 2, which are the use of the backup plate, the KTH method, vibration assisted drilling method. So there are some process variants, like one is simple drilling, in which we have a constant feed rate and the drill is making a hole in the composite laminate. But there are few process variants which help us to optimize our process by reducing the forces, improving the quality of the drilled hole, as well as reducing the drilling induced damage. So basically we have a set of inputs. You can see there is a wide variety of input, or the very versatile input that goes into the process, and the output is in terms of the forces and the damage. And then we have to take certain set of decisions which would help us to optimize our process so that we get a good quality hole. And finally we can vary our process a bit so that output is desirable or as per the requirement. And finally, what are the control parameters, what we need to control? The output we need to control so that we get a good quality hole. So we can control the thrust force and the damage criteria. So if suppose damage takes place beyond a particular level, we have to fine tune or tweak our process. And similarly, the thrust force goes beyond the particular limit, we need to adjust our input parameters, which will resultingly affect our process, and the process would then give us an output which would be within the limits or within the range. So this particular diagram, if you see, or this particular figure, gives us the complexity of the problem, which we need to understand before going into the next step in order to study or to investigate the drilling process using the different research tools. So first of all, we need to understand the need and the necessity of using the research tools. So here, in order to summarize the things, I want to emphasize that even so many input parameters are there, so many process variants are there, and different types of outputs are there. We cannot do experiments for each and every set of input, for each and every material, for each and every tool, for each and every tool geometry. So if we need to do these experiments, we can see, if you remember in the classification of thermosets and thermoplastic, there were so many polymers, and many polymers can be used as the matrix material. There is a wide variety of the fibers which can be used as the reinforcement. So there is a wide variety of composite materials which are prevalent or are being used in the industry in various applications. So there are so many materials, speeds and feeds can have a huge range, and as well as the drill point geometry, you can make your own drill point geometry, and we can investigate that how that geometry responds to the drilling process. So there is a large variety of input that exists, and the output has to be correlated to this particular input. So basically we cannot do experiment in each and every case, and therefore we need to develop certain models which once validated with the input parameters and gives the desired output can be used to simulate the behavior of the other types of materials, other types of tool geometries, and other type of operating variables. So once we develop a model, now suppose we develop a model for glass fiber, epoxy matrix. This is my workpiece material. I use the high speed steel tool as the cutting tool, and I select a particular range of the cutting speeds and the feed rate. So I have somehow made a case out of the total diagram that is there on your screen. So one particular case is the material is glass fiber, the matrix is epoxy. So my material parameters are fixed. The fiber type is glass, fiber volume fraction suppose 60%, stacking sequence is normal, all layers are made up of glass fiber only, and the matrix is epoxy. So glass fiber reinforced epoxy matrix, one material. Drill point geometry, suppose simple twist drill, drill diameter suppose 8 millimeter, drill material suppose high speed steel, and cutting speed and feed suppose I fix a range that cutting speed goes from V1 to V3 and feed rate goes from F1 to F3. Now this is one set of experiments that I will conduct with the conventional drilling process and record the thrust force and torque and the drilling induced damage. One set of experiments, and the output can be investigated to see that how the feed rate affects the thrust force, how the cutting speed affects the torque, how the, we can say, the drill diameter suppose we vary affects the output parameters such as thrust force, torque, and drilling induced damage. And this is one set of experiment. Now suppose the fiber type is different, is changed, fiber volume fraction is changed, stacking sequence is changed, matrix types is changed. So I have a wide variety of materials available with me. Now the drill point geometry can be changed. In one of the research papers, 17 different geometries have been investigated to study their influence on the drilling induced damage. So different types of tool geometries can be there, tool diameters can be there, and drill materials can be different. And similarly there is a wide range of speed and feed. Why I am emphasizing this point? Because we cannot do experiment for each and every set of parameters, because there exists a very big family of the composite materials and a very big family of the tool materials and a very big family of the tool geometries. So therefore we need to develop models which can be used to predict the behavior. But before the model can be used to predict the behavior, we have to validate that model with some of the experimental findings. So we cannot totally outperform the experimentation. Yes, we have to do the experimentation, we have to do rigorous experimentation, and the results of those experiments then have to be matched with the results of the models, and then finally when these models have been validated, these can be used for further prediction purposes. Then these models can be used to predict the thrust force, the torque or the damage without actually going for the experimentation. But for a very good model, the backbone is provided by the exhaustive experimentation. So now we will see one of the tools which is used in order to develop a model for prediction of suppose forces or the drilling induced damage. Finite element model for drilling of polymer matrix composites. Now what are the steps when we want to make a model? On your screen there are 5 to 6 different steps which have been mentioned, and these steps when executed properly, when performed in a systematical and logical manner, we would be able to develop a model which can be validated with the experimental results, and finally this model can be used for the prediction purposes or for investigating the drilling behavior, specifically in case of polymer composites. But these are the steps which are very general in nature. Any problem using the finite element method can be solved using these steps. We need to have a platform or a software or a finite element package, and in that package we have to first generate the geometry. As you can see the very first point on your screen, this is geometric modeling. So first of all we have to generate the geometry of that particular part that we want to analyze. So in our case, as we are investigating the drilling behavior of polymer composites, so our workpiece has to be modeled. So we will try to see it with the help of a diagram how the workpiece can be modeled. So first and the foremost point is to make the geometry of the workpiece. So once the geometry has been made, then it has to be discretized into finite elements. So the point number 2 is finite element generation. So we have to then discretize the complete geometry. It can be a 3-dimensional analysis, it can be a 2-dimensional analysis. So the geometry which has been modeled on this computer screen has to be discretized into different types of elements. Now these elements, there is an element library in the various packages from where we have to choose that which type of element suits our requirement. For example, when we are modeling a composite material, we have to select only that element which is suitable for modeling the composite materials. Why? Because in composite we have to make different layers. Suppose the laminate in which I am going to make a hole is made up of 4 layers. So the element should be such chosen so that this particular versatility is there in the element, or it has the capability to be modeled into 4 layers, and it has the capability to be modeled as a thick element. So during finite element generation, few important points have to be taken into account. So the first step is we have to make a geometry, and the second step is the discretization into the elements. Now the elements have to be such chosen so that it represents the actual problem in question. So the actual problem in our case is we have to model a composite laminate, and from the element library we have to choose only those elements which are able to take the properties of the composite materials, so that the fiber orientation can be given. As we know, in case of composite we can have unidirectional fibers, we can have bidirectional fibers, or the fibers can be randomly oriented. So we should only select those elements which has this capability to be modeled into a composite plate or a composite element. So finite element generation is done, the total geometry is divided into a large number of small elements. So these elements will combine together to depict the total geometry. So suppose we have in x direction 100 elements, y direction 100 elements, and in z direction another 50 elements. So we make a plate in which we have x a number of elements in x direction, number of elements in y direction, and number of elements in the z direction. So we have now discretized the total structure or the total or the plate or the geometry which we have modeled into various elements. So first point is geometric modeling, second point is discretization into finite elements. Point number 3 on your screen is boundary conditions. Now we have to make a hole inside a composite laminate. The laminate should not move, or the material or the raw material should not move, because when the drilling action is taking place, the plate should be fixed on the table, which is an actual requirement when we are making a hole on the machine. Now here we are trying to develop a model. In this model, one of the prerequisites is that the plate should not move, because it will represent the actual drilling which is being done on the machine. Now we have to fix the plate. Now when this composite laminate or the polymer matrix composite material has to be fixed on the plate, has to be fixed on the table of the workpiece, we have to constrain the movement of this laminate into x, y and z direction. Moreover, it should not rotate. So the process of providing the constraints to the workpiece or to the geometry that we have modeled is falling under the broad umbrella of boundary conditions. So we will provide the constraint in x direction, y direction and z direction, and it will restrict the movement of the plate in x, y and z direction. So that is one set of boundary conditions, that the plate is fixed. Another set of boundary conditions is that the drill should come down. The drill should rotate, it should come down, it should interact with the material, and finally it should be removing the material in the form of chips, and finally it should be able to generate the hole. So all these conditions will fall under the boundary conditions. We have to specify the speed at which the drill will rotate, we have to specify how the drill will go down, we have to specify how the drill will interact with the workpiece material, how the material flow will take place. So all this, how the material flow will take place is certainly at a later stage, but first of all we have to specify these boundary conditions, like the plate will not move, point number 1. Point number 2, the drill will rotate, that is rotation has to be provided. Point number 3, the drill will translate and it will come and touch the workpiece. So all these conditions, when they are given, they fall under the category of boundary conditions. So till now we have seen the 3 very important points of problem building, where we are building our problem, where we are trying to model what is actually happening on the machine. So what we are doing? We have a geometric modeling in which we are making the geometry of our workpiece. Our workpiece is a composite laminate, it is a flat plate. So we have a composite laminate. Now we are discretizing into various elements. From the element library, we are only choosing those elements which correspond to the composite properties, or which have the property to be modeled as a composite element. And finally we are specifying the boundary conditions, that the plate is fixed and the drill is coming from top and making a hole. The drill is rotating as well as it is coming down. Then we have to provide the data for analysis, in which we have to provide the material specification. Suppose in finite element generation we have specified that the laminate is having 4 layers. Now for 4 layers, topmost layer suppose has glass fiber, layer number 2 again has glass fiber, and 3, 4 also have glass fiber, so the task becomes easy. But suppose all the layers are made up of different materials, so in data for analysis on your screen the material specification has to be given, fiber orientation has to be given, and the lamination sequence has to be provided. So we have to now provide the data that this particular laminate, which has been discretized using this element, is made up of this material. The lamination sequence is this, different layers are made up of different materials or of the same material. The fiber orientation in the different layers is same or different. If different, then what is the fiber orientation? All these particular inputs have to be provided in the data for analysis stage. And finally, once we have set the problem by setting the geometry, by discretizing the geometry into finite elements, by providing the boundary conditions and the relevant data related to the material, related to the tool material. When all this data has been provided, we will execute the program, and once the program is executed, it would run. Lot of calculations will be done, matrix multiplications will be done, and we will get the output in terms of the stress plots or the strain plots, or sometimes displacement, or in many cases we may get some specific failure criteria plots which will help us to find out that whether the damage has taken place or not. So we will see some of the plots where we will see the damage has taken place. And finally, once we see the output, the stress contour plots or the contour plots of the various parameters, we would be able to correlate what has happened actually when the experiments were done and what has happened when the model has been executed. So now we will see how the results can be analyzed. The process of modeling or the process of setting up the problem has been discussed in this particular slide. So once again, before closing down this slide, we can see that these are the important steps to set up a problem and to execute a problem and to analyze the results. So the steps involved are the geometric modeling, finite element discretization or finite element generation, boundary conditions, data for analysis. Now material data has to be provided and the tool data has to be provided specifically for our case. Then the program has to be executed and the results have to be finally analyzed. So here you can see the models of the various drill point geometries. This is the model which can be modeled in any geometric modeling software. This is one model, or this is a tree panning tool, and this is the actual tree panning tool. This is, you can see, this is a parabolic point drill, and here is the representation, software representation or the model of the parabolic point. Here we can see this is a twist drill, simple twist drill, and this is the model of the twist drill, and this is a jaw point or the jaw drill, and here we see the model of the jaw drill. So first and foremost, we have to make a model, and any geometric modeling software can be used for making these models. Now on your screen you can see the output. One of the outputs is shown here. This red area indicates this is a failure plot, and we can see the red portion is indicating a value which is more than 1. It is precisely 1.995, and this red portion and this pink portion is 1.831. So wherever this red and pink portions are there, it means the damage has taken place at that place. So basically this is the geometric model, step number 1. This is the geometric model where a hole has to be generated. So this particular analysis was done with a pre-drilled hole. It was assumed that there is a pre-drilled hole which already exists in the laminate, and this particular hole has to be enlarged depending upon the final diameter requirement. So the hole has to be enlarged using a standard drill point. So this is the geometry of the laminate, and these blue points indicate that this particular laminate cannot move in X, Y and Z direction. So this particular laminate is fixed. It cannot move in X, Y and Z direction. Therefore, we can very easily assume that this particular laminate is fixed on the bed of the table, and it is not able to move in X, Y or Z direction. It cannot move. So it is fixed, and which we have ascertained by providing the boundary conditions as is visible on your screen. So these blue dots indicate that this particular laminate cannot move in X, Y and Z direction, and then the input other boundary conditions are given, and finally the results or the contour plots are seen as on your screen, that the damage has certainly taken place. So the rotations at which the drill was rotating and the feed rate at which the drill was translating or the drill was performing the hole making operation or the drilling operation. So the combination of cutting speed and feed rate with that particular drill point geometry which was used would certainly lead to damage in this particular material. So this material was glass fiber reinforced plastic material. So for glass fiber reinforced plastic material, yes, there is bound to be certain damage that would take place. We can see there are few more results of the damage which has taken place, and here we can see, as I have already emphasized on the slide number 1, we have seen that drilling of polymer composites is a very, we can say, complex process in which there are so many input parameters and the output has to be governed so that we make a whole which is good quality. So here we can see when we have the experimental results, this is a result of an experiment, so we can correlate it with the results of the finite element, and we can find out that whether the damage which is being predicted by the finite element method correlates with what has been recorded using the experimentation. So this has been recorded using experimentation, this has been predicted using the finite element model, and we can correlate the two. Here also we can see the two can be correlated, although this is a magnified view just to highlight the damage area, so we cannot say one-to-one matching here, but we can see the qualitatively the areas are damaged around the hole, and here also we can see the damage has been reported or predicted using the finite element method. Here we can see damage is there, here also lesser damage, here also lesser damage, more damage has been found experimentally. Under similar set of conditions, more damage has been predicted using the finite element method. So where we can emphasize one important point, that when we have a strong experimental base, we have conducted a lot of experiments that can be used as input, and we can model the process, and the results of the model can then be validated with the findings of the experimental results, and then we can use this particular model now by varying the various input parameters and predicting the damage as well as operating the optimal operating variables at which the minimum damage is taking place. Then we come to another aspect of our module 5 in which module 7, in which we have seen there are two broad categories of processes which fall under the secondary processing, that is the machining or drilling and the joining. So now we will briefly overview that how the process of microwave joining be modeled, so that we are able to find out that whether the two pieces that we want to join using the microwave energy can be joined together or not. Here also we can use a software platform to model the process and find out the temperature which is generated at the interface of the two composite laminates or two composite adherents that we want to join together. So in microwave joining, three-dimensional finite element model can be developed using softwares to simulate the joining process. Now what are the steps involved? Again, to revise, the steps involved are same. We can undertake these steps sequentially in order to achieve our objective. So what are the steps involved? I will just read out the steps because we have already discussed these steps in detail while we were seeing the modeling of the drilling process. So these steps are geometric modeling, number 1, again the finite element generation, boundary conditions have to be specified, then the data for analysis has to be given, and finally the execution of the program and analysis of the output. So material specification, fiber orientation, all this has to be specified depending upon the composite adherents that we are using. Boundary conditions in the previous case were in terms of the rotation of the drill, the feed rate was specified, the plate was constrained. Here the boundary conditions can be in terms of the wattage or the power that we are putting as an input, it can be in terms of the exposure time for which the composite adherents have been exposed to the microwave radiation. So the boundary conditions will change depending upon the problem at hand. Now whatever problem we have at hand, accordingly we will set the boundary conditions. So here our purpose now is to form a good quality joint or good quality bond between the two composite adherents, and the source of energy is the microwave energy. So quickly we will see the type of output that we will get. Now in one of the steps we have to specify the data for analysis. So here we have to put electromagnetic parameters and the heat transfer parameters as the input into the model, so that the model gives us the results which are close to the experimental results. So we will not discuss these points. These are some of the parameters which have to be put as an input into the model so that we get the desired output. Now this is actually the simulation process. Here there are two adherents. This is adherent number 1, this dotted portion. You can see how the arrow is moving. This is adherent number 1 and this is adherent number 2. So we have two adherents standing end to end like this. We have two adherents. Other view can be like this. This is top adherent, this is bottom adherent. So we have two adherents like this, and this is the top of the adherent. So when we have adherent number 1, this is adherent number 1 and this is adherent number 2. So 1 and 2, there are two adherents, and finally we have put a susceptor here to accelerate the rate of heating. This is a susceptor, and the joint will form over this bond area. This dotted circle indicates the joint interface where the joining would take place. On this side also we can see actual finite element result plot or a contour plot which indicates that the temperature is higher in that particular zone and the joining is going to take place. Now here we can see this is a three-dimensional model. Just briefly we can see what type of output we get. We can get output in terms of the electric field deformation inside the cavity and the surface temperature variation. This is now the microwave total cavity. These are the two adherents which have been kept together, and this is the input port, and we can get the output, that what is the temperature which is being generated at specific locations inside the microwave cavity. And if the temperature at the interface or at the joint area or the bond area is more than the critical temperature which is required by the polymer to form the joint, then the joining would certainly take place. Now here we can see on your screen temperature variation with time at the center point of the joint interface. So the temperature is unilaterally increasing with the passage of time. Now this is the exposure time for which the microwaves have been impinged on the joint area. So microwaves are impinged over the whole microwave cavity, but we focus specifically on the bond area by putting some susceptor element which would absorb the microwaves and focus the heat at a particular area, and the other areas can be made opaque to the microwaves. So basically we are focused in joining. Our focus in case of joining is in the area where the two adherents are bound to be joined or where the bond has to be formed. So in that particular area we want to see that how much temperature is being generated because of the microwaves. So this is showing the temperature variation with time at the center point of the interface. So we can see temperature is increasing when the exposure to microwaves, the time for exposure to microwaves is increasing. So at a particular time, suppose 250 seconds, at 250 seconds we have a temperature more than 100 degrees centigrade. So suppose 100 degrees centigrade is a temperature at which the matrix material has the tendency to form or to we can say soften a bit and join with the other matrix that is there on the other adherent. When there is a tendency that the matrix will soften and form a joint at suppose 100 degree centigrade, we can say that at 250 seconds of exposure and a particular wattage, suppose 900 watt of input setting, 250 seconds of exposure, the temperature is more than 100, which is more than the bonding temperature for a particular matrix, for a particular polymer, at which the polymer has the tendency to soften and form a bond with the other adherent. At that particular temperature the bonding would take place. So we can very easily see, we can predict the exposure time at which the bonding is going to take place. So we can see that finite element method, and there are other tools as well that we would be seeing in the subsequent slide, are the tools which help us to investigate the various important facets or various important aspects of this particular area of secondary processing of composite materials. And finally, we come to the last part of our lecture, that is the soft computing techniques to investigate the drilling behavior of PMCs. Now, we have seen in the very first slide today that the drilling process, there are so many inputs and so many outputs. Now, somehow we have to correlate the inputs with the outputs so that we are able to predict for a certain set of inputs what would be the output. So, for that there are so many soft computing techniques which have been developed worldwide and are being used in order to correlate the input parameters with the output parameters. Some of the well known techniques are the artificial neural network, the genetic algorithm, hybrid neural genetic algorithm GAANN, fuzzy logic, hybrid neurofuzzy or the ANFIS system. So, these are some of the soft computing techniques which are used to correlate the input to the output so that for a specific set of inputs we are very easily able to predict that what would be the output. But certainly these methods or these techniques are based on the experimental results. First, we have to undertake exhaustive experimentation in order to train these methods or to intelligently train these methods so that they can further be used or their intelligence can be used to generate the output for an unknown set of input parameters. But first we have to train them with a known set of input parameters so that they develop the intelligence which can further be used for unknown set of input parameters, and finally we get a desired output out of these intelligence tools. So, this is an artificial neural network. So, in artificial neural network we can see there are a set of inputs 1, 2 and 3. There can be other inputs as well, more inputs can be used and we get the output. So, this is the intelligence that is inbuilt, and this intelligence is developed by giving a set of input data. The data has to be huge, it has to be have a wide range so that the network gets trained better, and once the network gets trained better, then for unknown data inputs also specifically within the range it should be able to give us the output. Now, suppose let me take an example. In our case, drilling of polymer composites, we have suppose 4 input parameters: cutting speed, feed rate, drill point geometry and the drill diameter. Suppose these are the 4 input parameters that go into the network. Output is suppose the drilling induced damage. Now, for these 4 input parameters we have to take these parameters at different levels and perform a lot of experiments, which would be the output has to be found out for these experiments in the form of drilling induced damage. So, we will do a large number of experiments, and for these experiments we will record the drilling induced damage as the output, and this data, the input output combination data, would be given as an input to this particular model. And finally, when it is trained properly, we would be able to find out the drilling induced damage for a specific set of input parameters for which we may not have done the experiments. So, this particular model will help us to find out before doing the experiments that how much damage is going to take place for this set of input parameters, for suppose cutting speed V1, feed rate F2, drill geometry D3 and drill diameter 8 millimeter. So, for these set of input parameters, what is going to be the drilling induced damage, and these are the 4 inputs which were not taken for training of the network. The network was trained with a different sets of input. So, we can see that once this is done, we are very easily able to find out that how much damage is going to take place. So, this is just one example of a one particular technique. As we have seen in the previous slide, there are large number of techniques which can be used to do this type of a work. So, with this we come to the end of our course, that is processing of non-metals, and we are finishing today the module number 7, in which we have seen different aspects of the secondary processing of composite materials. We have seen the drilling aspects, the issues and challenges in the drilling aspects, the process variants of the drilling process, or the different tools and techniques which are used for making holes in composite laminates, which are one or the other process variant of the actual drilling process that we have seen. Then we have seen the joining of composite adherents using adhesive bonding as well as the mechanical fastening. What are the issues and challenges related to the joining of polymer composites was seen. In lecture number 4, we have seen the microwave joining of polymer matrix composites, and finally today in lecture number 5 of module 7, we have seen the finite element method as a tool for conducting research in the area of polymer matrix composites, specifically the secondary processing of polymer matrix composites. And we have seen that there are some tools, artificial intelligence tools, which can be used for predicting the process outcomes, specifically in case of drilling of polymer matrix composites. I hope you have enjoyed this series of lectures on processing of non-metals. Thank you.